my name is Tasnim. This is my hybridization project. My molecule is xenon difluoride. I'll be explaining Lewis dot diagram, condensed electron configuration, condensed energy diagram, hybridization, and VSEPR for my molecule. Later on, I'll be explaining intramolecular force to identify any special bond in my molecule and intermolecular force to explain melting point and state of my molecule in comparison to water at room temperature. Firstly, we need to draw a Lewis dot diagram. A Lewis diagram shows how the valence electrons are arranged among atoms in a molecule. The molecule xenon difluoride consists of a central atom surrounded by other atoms. The central position is occupied by atom with highest bond capacity or the atom with smallest electronegativity. Here xenon belongs to group 18, which is the central atom. To draw the Lewis dot diagram, we need to determine the need and half number. The need number is basically the maximum number of electrons the elements in the compound can have to form a full octet. The half number is the number of electrons present in the valence shell of the element. Fluorine has 7 electrons. So the half number is 22. This is my Lewis structure, but it's not complete yet. From the half number, we need to subtract shared pair of electrons. In this case, there are 2 bonds, so 2 electrons for each bond, and we subtract 4 for the 2 bonds. Then we subtract the total number of electrons around 2 fluorines to get the lone pair of the central atom. Each fluorine has 6 electrons, and 2 fluorines has a total of 12 electrons. Xenon has 6 electrons as lone pair. Now we need to find the condensed electron configuration. For xenon, krypton is the nearest noble gas before xenon. The condensed energy level diagram is our next step. The lowest energy orbital are filled first, 5s, (4d) is higher than 5s. Filling up before down. Now, hybridization. The hybridization theory explains the bonding in molecules that do not fit into the valence Bond theory. The central atom makes new orbitals before bonding with the other atom. It's like creating an average by combining the atomic orbitals. To determine whether the compound has sigma bond, lone pair, pi bond, and coordinate covalent bond, we need to look at the Lewis structure. Look at the surrounding atom of the central atom. If the valence electron of surrounding atom matches with the lone pairs of surrounding atom that can be seen in the Lewis diagram, then it is a coordinate covalent bond. Here, the central atom xenon is surrounded by two fluorines. According to the Lewis diagram, fluorine has 3 lone pairs around it, but according to the periodic table, we know that group 17 elements are halogen and has 7 valence electrons, so it is not coordinate covalent bond. Rather, it's a sigma bond. Xenon has 3 lone pairs around it. Under hybridization, we write according to the writing order. First sigma bond, then lone pair, then coordinate covalent, and then pi bond. For sigma bond, we draw one hybrid orbital with one electron. There are a total of 5 hybrid orbitals. As there is 2 sigma bond, so we draw one hybrid orbital with one electron. Next one, in the same way. For lone pairs, we draw one hybrid orbital with 2 electrons. As there are 3 lone pairs, so we draw one hybrid orbital with 2 electrons. And the lone pairs has 3 hybrid orbitals. Now we will name the hybrid orbital. First, we'll write the energy level number, which is 5 in this case, because the highest energy level is 5. There are 2 sigma bond and 3 lone pairs, so xenon difluoride needs 5 hybrid orbital in total, as we said. One, 2, 3, 4, and 5. Its name will be 5s PQD. Now Vesper. We again need to draw the Lewis structure for it. There is 5 electron groups. Look at the central atom xenon. There are 5 electron groups. While counting the electron groups, the bonding pairs and lone pairs in central atom are counted to predict the geometry. This compound has 2 bonding pair and 3 lone pair. So, geometry has 2 BP bonding pair and 3 lone pair. So the geometry will be trigonal bipyramidal. We'll now predict the shape of it. If you look at this, we'll see that Molecule with 2 bonding pair and 3 lone pair has a linear structure. The shape here is linear. The angle is formed from bond to bond. So the angle here is 180 degrees. Now let's summarize intramolecular and intermolecular force of this molecule. Intramolecular force, attraction force, forces within bonds that hold atoms together in molecules. Types of intramolecular forces are ionic, covalent, metallic. In grade 11, we learned about electronegativity. To predict whether chemical bond between two atoms will be ionic, polar, covalent, or covalent, the electronegativity difference between elements involved is considered. I got this periodic table from grade 11. Here we can see xenon has electronegativity 2.6 and fluorine has 4.0. So we'll find electronegativity difference. Bonds with electronegativity that are between 0.4 to 1.7 are polar covalent. So xenon difluoride has covalent bonds between xenon and fluorine. The sharing of electrons between xenon and fluorine results in this bond. As the electronegativity difference is 1.4, so it's between 0.4 and 1.7 is polar covalent. Now, let's note down what we found. I've drawn the Lewis structure again. We need to now know whether this molecule is symmetrical or asymmetrical, whether it has a dipole or not. The criteria of symmetry is all the bonds have to be equal, no lone pair around central atom. The central atom has lone pairs, so it is not symmetrical. A molecule that has a dipole should satisfy the following. It should have at least one bond that is polar. It should not be symmetrical. The bonds are not the same. The central atom has a lone pair. If these two criteria are fulfilled, that means it is not symmetrical. It has bonds that is polar. The central atom has lone pair electrons, and the bonds. In summary, the central atom has lone pairs and each xenon-fluorine bond is polar. However, the molecule xenon difluoride as a whole is not polar because it has no dipole. And how is this? This molecule when we look at the shape, we see that two fluorine atoms placed 180 degrees apart from each other. And xenon has 3 lone pairs. Both dipoles being equal and opposite direction cancel each other due to the linear structure, which means the whole molecule becomes nonpolar. That's why it is not polar. Again, this molecule does not have any special bond like coordinate covalent or resonance structure. Coordinate covalent it does not have because it has sigma bond. Resonance only occurs when a molecule has at least one double bond, as xenon is connected to two fluorines with single bond or sigma bond, so it has no resonance structure. Now let's understand intermolecular first. Intermolecular force are attraction forces between molecules that help molecules experience attraction for each other. Their types are lengthy dispersion and temporary dipole attraction, permanent dipole attraction, and hydrogen bonds. Lengthy dispersion, very weak because the instantaneous dipoles exist only for a moment and only when the particles are very close to each other. It increases as the number of electrons at the surface area of the atom increases. Dipole-dipole occur between polar molecules. Van der Waals force is a term collectively refers to these weak forces of attraction. Van der Waals force common term for lengthy dispersion and dipole attraction. Hydrogen bond is when hydrogen atoms are bonded to extremely electronegative atoms, such as fluorine, oxygen, or nitrogen. Extremely polar and strong intermolecular force it is. If we look at the periodic table again, we'll do some calculations here. We already found that xenon difluoride has electronegativity 1.4 and xenon fluoride has polar covalent bond between them, although the molecule as a whole is nonpolar. But due to this electronegativity difference, it is considered to be a polar covalent. And we already got that it has no dipole. From here, as we see, a molecule which has no dipole has only lengthy dispersion force as intermolecular force, which is very weak. If we do the same thing for water, we'll see the electronegativity difference is oxygen 3.5, hydrogen 2.1, and the difference is also 1.4. Which is also polar covalent. And as the hydrogen is bonding with extremely electronegative atoms such as oxygen, so it has hydrogen bonds. Oxygen is extremely electronegative, which is bonded with hydrogen, so this molecule has hydrogen bond along with dipole-dipole and lengthy dispersion. hydrogen bond is a very strong intermolecular force. On the other hand, xenon difluoride has London dispersion force which is much weaker. But the size of xenon difluoride molecule is larger than water, and as the size of the molecule increases, the intermolecular attractions become stronger. If you look at the physical properties of covalent substances, we know that when ionic compound melts, attraction between all ions is overcome. When covalent melts, relatively weak intermolecular forces are overcome, and less energy is required to overcome these attractions. Covalent compounds have low melting and boiling points. As the size of the molecule increases, the intermolecular attractions become stronger. If we particularly look at group 17, we'll see that as we go from top to bottom of the group, the size of the atom increases. From fluorine to iodine, it increases. And here, the melting point also increases. From fluorine, it was negative 220 degrees Celsius. Chlorine, it becomes negative 101 degrees Celsius. When it comes to bromine, it becomes negative 7.2 degrees Celsius, and iodine 114 degrees Celsius, acetylene 302 degrees Celsius. So the more we move from top to bottom in a group, the melting point gradually increases as the size of the molecule increases. At room temperature, the melting point and boiling point also increases as the size of the molecule increases. If you look at this xenon difluoride and water molecule, we see that xenon difluoride is much more bigger. Xenon difluoride, despite having London dispersion force, is at higher melting point because it is a larger molecule. This molecule is solid at room temperature because its mass is more and the number of electrons is higher. So it has stronger London dispersion force. In conclusion, we can say that the melting point higher than water at room temperature, state is solid at room temperature. Thank you.